Charles' Law, page 4 in your packets. So, Charles' Law, what it states is this, that we could take the volume and the temperature and demonstrate them to have a directly proportional relationship. Now, how do we do that? Well, we say this. V of 1, T of 1 equals V2 over T2. Now, some people refer, just like I told you with Boyle's Law, V initial over T initial equals V final over T final. It does not matter as long as you put the initials here and the finals there. Call them 1 and 2. Call them A and B for all I care. But that is the relationship. Now, just to give myself some space and get rid of that. So again, what we want to note about it is a couple of things. Number one, directly proportional. What that means is this. If I take the volume and I double it, then the temperature is likewise also going to double, directly proportional. Or the more likely thing is, if we took the temperature and increased it, we'd also increase the volume. Okay? A couple of other quirks about it. T must be in Kelvin. There's a reason for that, right? Okay? The reason that temperature must be in Kelvin is because we're going to use this as a denominator to be able to divide. And Kelvin does something for us. It takes away negative values. It only allows us to have things be positive. Because otherwise, positive 7 degrees and negative 7 degrees would be a disaster from a standpoint of trying to do the math. These things are 14 degrees apart, but when you do the math, they'd be treated the same other than a sign. And that's not right, and that's not good. So because of that, temperatures must be in Kelvin. And the other thing you have to have is your volumes must match. What do I mean by that? If this volume is in liters, this one has to be in liters. If this one's in centimeters cubed, centimeters cubed. Milliliters, milliliters, I think you get the point. So directly proportional. Temperature must be in Kelvin, volumes must match. So let's go ahead and do a couple of examples. So number 1 says on page 4, if I have 45.00 liters of helium in a balloon at 25 degrees Celsius, so my volume is 45.00 liters over 25 degrees Celsius. Well, that's not in Kelvin, is it? So in order to take 25 degrees Celsius and turn it into Kelvin, you have to do this, right? K equals 273.15 plus degrees C, right? So that ends up being 298.15 Kelvin. Note, no degree symbol. Kelvin is not expressed in degrees. So this is 298.15 K. Equals, well, as we read the problem, it says, and increase the temperature to 55 degrees Celsius. Now, for time purposes, I'm going to just say, so 55 degrees, what that means is we would have taken and added 273.15 plus 55 instead of 25. So when we do that, that ends up being 328.15 Kelvin. Again, this would just be 55, therefore you put that in there, and you would get 328.15. Now, on to space, so I'm going to get rid of that. We're going to solve this for volume. Now, when you have something like this, what you do is you cross multiply. So the algebra ends up being this. 298.15 times V equals 45.00 times 328.15. Then you would divide both sides by 298.15 to isolate the V, right? Because that would be the algebra. And you get V equals. When you do this, you're going to get an answer that is 49.53. Now, the reason I answered this with 4 significant figures is because when I go look at my numbers, well, that one right there has 4 significant figures. This one has 5 significant figures. This one has 5 significant figures. Well, here we're doing multiplication, aren't we? So therefore, it's determined by the least number of sig figs, 4, 4. That was number 1. Let's go ahead now and do another one. Sorry, I got rid of that real quick. Let's put it back. Volumes must match. We don't forget about that. Okay, number 2. Number 2 says calcium carbonate decomposes at 1200.0 degrees Celsius. So I'm going to save myself a little bit of time. I'm just going to tell you 1200 degrees Celsius becomes 1473.15 Kelvin. Just using the exact same equation we used just now. If 25 liters are collected at 1200, 1473.15, so we have 25.00 liters that was collected at 1473.15 Kelvin. What will the volume of this gas be after it cools down to all the way to 25 degrees Celsius, which we did on the last problem as 298.15 Kelvin. So that's 298.15 Kelvin. You cross multiply, do your algebra, and you get V equals 4 sig figs, 6 sig figs, 5 sig figs, therefore 4 in your answer. The answer is 5.060 liters. All right, next. Number 3. Number 3 says, okay, if I have 130.00 liters, so 5 significant figures, that's the volume, and a temperature of 250 degrees Celsius, which will become 500 and I think it's 523.15 Kelvin, equals. If I cool the gas until the volume decreases to 85.00 liters, what is the new temperature? Now I tell you, temperatures are kind of a drag. And so what I'm going to do on temperatures, and I'll say this in class, is I'm not going to be a real stickler on significant figures. I'm just going to more want you to get the right answer. What I'm always usually going to do is, since there's 5 significant figures in this temperature, I'll probably make them match that. All right? It's weird because sometimes when you convert in and out of Kelvin, you end up going from something like 4 significant figures, or like in the problem, 250 degrees Celsius actually only has 2 significant figures, right? So temperature is just kind of weird. So what I'm going to do is I'm just going to make it match the other one. So I do my cross multiplying, right? And then I isolate T, and I get T equals. And what I have is 342.06 Kelvin. Now for me, that's not good enough. And what I mean by that is this. In the problem, you were told 250 degrees Celsius, and you converted it to that. Here is something I am going to expect. Your answer must match the units that was given. So if I gave it to you in Celsius, you got to give it back to me in Celsius. So you take that, you turn it back into Celsius, and so what I did was I said, okay, I'm going to give 68.91 degrees Celsius. And again, I'm not going to be a stickler on significant figures here. If you gave me 68.91 and another number, I guess you could, but the fact of the matter is when you take this, right, and you subtract 273.15 from it, that's what you end up getting. So that's the answer I gave. Again, I'm not going to be a terrible stickler on significant figures. Okay? You know, big thing I want to make sure that you're making note of. Notice here, your volume is in liters. Your volume is in liters. There will be problems that will come up later where the units will not match, and you will have to make them match before you put them in the calculation. That's Charles' Law.